So welcome to Stat 479 Lecture 8. So we're in the middle of discussing this next class of models, which is generalized linear models. And remember that the reason that we look at this is because we're interested in kind of the supervised multivariate setting, where we're considering different data types that go beyond what we saw for the standard linear models with linear regression. So in the previous lecture, we kind of took a deep dive into exponential families because they are really the fundamental building block of these generalized linear models. So I'm just going to quickly recap exponential families and remind people of the properties of exponential families, which will be used today and are generally useful when we talk about generalized linear models. That'll lead into the actual definition of our generalized linear models, which are based on exponential families. Then we'll actually talk a little bit about kind of how we find solutions or how we find estimators for these generalized linear models. And in particular, I'll talk about maximum likelihood and how this sort of very naturally and nicely connects to convex optimization, which will be useful when we talk about kind of how to actually find estimate or how to find the maximum likelihood estimate. So just as a recap or a reminder of exponential family distributions, so remember that exponential family distributions are distributions that have this form. So there's y, which is kind of the random variable, and so y is the kind of main argument of the distribution, and theta is like your parameter of interest, in particular the natural parameter. And we talked about the connection between kind of natural and mean parameters in the previous lecture. Here we're really specifically referring to the natural parameter because that's what we're going to use to define generalized linear models. So, the exponential family distribution has this form and it's exponential because there's an exponential in it. And there's four key components here, which we've touched on already. There's the base measure or base distribution, h of y. There's the sufficient statistic, t of y, the natural parameter theta, and the log partition function. And the log partition function is probably the function that really carries the most information about this distribution. If you kind of know that, then that tells you a lot about the distribution. So just some properties that we discussed in the previous lecture that we're again going to use today. So the first thing is if we let mu equal to the expectation of t of y, then we know that that's the first derivative of a with respect to theta. And so mu is actually the mean parameter. And remember how we spoke about kind of these two different ways to parameterize the distributions through the mean parameter and the natural parameter. And they're connected through this first property. The second property gives a formula for the variance. So the variance very conveniently ends up being the second derivative of a. And then the other property, which is probably the most important property, which is related to that second property, says that a theta is a strictly convex function. And so what that means is that a prime prime, or the double derivative of a with respect to theta, is strictly greater than 0. Okay, and so remember that so this is going to be the segue or the building block for generalized linear models. So a couple of lectures ago, we kind of introduced this concept, but didn't really have the building blocks of exponential families yet, or we didn't really have an understanding of that key building block. And so, given that we now have that building block, we can kind of properly define it and kind of go into a little bit more detail about generalized linear models using what we know about exponential families. So remember again that, in this general framework, we have the data, which remember is that okay, so we have this is supervised data, and I'm going to use this notation here to say that x of I is in R to the P, where so you can think of this as just for each sample there's p covariates, and we're talking about multivariate statistics here. So there's p covariates, and so we can think of x of I is for each sample there's a p-dimensional vector which represents its covariates or its features. So we have xi is in r to the p for I equals 1 to up to n. Okay, and so you can think of your data as being where xi is in r to the p and yi is in r, and you repeat this n times. So it's kind of the same data that we had for the linear when we were talking about linear models and linear regressions. But what's different here? The difference is that So the general idea of why we introduce generalized linear models is we want to kind of go into more general data types. So we're letting yi kind of be any data type. So it could be Bernoulli or a binary, which is 0 or 1 to say an event occurs or it doesn't occur. Or it could be like an integer if you're counting the number of events like earthquakes. And so this is kind of why we go from linear models to generalized linear models, because as we'll see, the exponential families give us more freedom to look at a broader class of distributions. And so the next thing we're going to focus on is this data generating model. So this is the second component of our statistical framework, and this is where we use the idea of exponential families. So we're going to let this denote an exponential family distribution that we defined earlier. And so we have that yi has the distribution. So for the GLM p of yi, and then given, so let me just talk through this a little bit. So this is like your theta of I. B is in r to the p is the parameter of interest. Okay, so remember that we have this natural parameter, but this natural parameter now is allowed to change with I as a function of this of these covariates. So the covariate information basically allows us to change the theta I, but we still have this coefficient vector b, which is constant. And so we can, if you kind of want to see this not in vector notation, this is just simply that xi transpose b is just sum j equals 1 to p xji bj. So this is our theta of I. Okay, and so this is just the definition of the generalized linear model. So let's look at a couple of examples. So one example we can consider is this is the standard linear model that we've actually already seen, and so this is one example of this, which we'll see, which is that if you have the other thing I should mention here is that yi's are independent. Okay, so if you know the xi's, the yi's are independent. So this is going to be crucial when we talk about maximum likelihood estimation. So remember that, so for the standard linear model, this is one example. Remember that one example of P was a normal distribution. And so what that is that the mean, so we have that sigma squared is a known constant. And then the mean equals xi transpose b, or you can think about it. And so this is, the theta and the mu are the same for the normal distribution. And so okay, and so this is exactly what we saw in the. We actually considered this example already when we were looking at linear models. So okay, so this is not really kind of telling us anything new, but the thing that remember that this is a generalized linear model. So one special case of it is what we've already learned, which is kind of the standard linear model. But the whole point is that of introducing this is that we can go beyond that. So let's see what happens when we kind of plug in some other distributions. You can imagine plugging in the Bernoulli. So the Bernoulli P distribution, and remember that we want to use the natural parameter form of this. So we know that we have this relationship that P equals 1 over 1 plus e to the negative theta here. So in natural parameter form, we have that, okay, and so for the GLM, what this means is that y is going to be Bernoulli distributed with the probability being 1 over 1 plus e to the negative xi transpose b. And remember again that and this is, I just want to remind everyone why this natural parameter form is so useful here, because you can see that P is typically going to be between 0 and 1. We have a lot of different P's here, and they depend on these covariates xi and b, which could be kind of any real numbers. But because we're using the natural parameter, it doesn't matter what xi transpose b here. This mapping into 1 over 1 plus e to the negative theta ensures that regardless of what xi and b are, you're always going to get a number between 0 and 1. So P is always going to be between 0 and 1, no matter how you choose, how you end up, choosing your theta. So remember that theta I here is xi transpose b. So any values give valid probability. And so this is kind of why we went to all that trouble of introducing these exponential families, or one of the reasons why we went into all that trouble of introducing these exponential families, because they give us this, very general set of distributions, and you now sort of don't have to worry about making sure that your x's and betas lie in a specific, or your x's and b's lie in a specific range. And so we'll do another example. Which was the Poisson lambda distribution. And so remember again, when lambda was the mean parameter and was related to the natural parameter theta through e to the theta. So we had that, in the natural parameter form, so we're going to have a Poisson distribution, but the lambda is now e to the theta. And once again, note that no matter what you choose for theta, your e to the theta is always bigger than 0, whether theta, like whatever value theta is. So you're always going to be in a valid range. And so for the GLM, what we get is that yi is distributed Poisson e to the xi transpose b, so we have the theta I here. So just try to keep track of what's the natural parameter, what's the that we're estimating, and just to kind of keep track of what's going on. I know there's a lot of notation here. So this covers two. So the second component of our general framework, which is defining the data generating distribution that we have for these various examples. So now we turn our attention to 3. So we're going to really talk about that for the rest of this lecture, and potentially going into the next lecture as well. So we know that and so the question that we're interested in is how do we estimate B from data? So this is kind of the key question. So we have our data x1 through to xn and y1 through to yn, and how do we estimate our B from data? So this really focuses on the estimator estimator or algorithms that we have here. And so when you kind of completely know the distribution, which we do in this case, because we know that it's a natural parameter exponential family and we know which exponential family it is, the most natural thing to do is to do maximum likelihood estimation. Okay, so how does maximum likelihood estimation work? We have that we want to maximize the likelihood, so we're maximizing over B, and then we're looking at the probability Okay, and this follows by independence. So because we assumed independence, that's why we get this product of several different several different distributions. Okay, and so we're trying to maximize the likelihood, but because we're in the exponential family, we have a lot of kind of extra information that we can use here. So we know the form of this distribution looks like this. Okay, so here what we have is that this is like your theta of I, and this is like your theta of I here. And so this is why we end up with this form. So remember that this is just using exactly the form for the natural parameter exponential family distribution. Okay, and so we know that we also know that this base measure or base distribution plays no role because it doesn't involve B at all. So we can re-express this just as we did in the previous lecture when we looked at just maximum likelihood in the univariate case for exponential families. This works out very nicely to just the product just becomes the sum when you move it into the exponential. So you get okay, so so I should say that this whole thing has a sum around it. So this is the thing we have to maximize, and we also know that we can do what we typically do in these scenarios, which is to take the negative and the log, which means the max becomes a min, and then we take negative log. So we end up with this objective here in terms of the okay, so this is the objective that this is the objective. I'm going to use this notation here. This is the objective we seek to minimize. So maximum likelihood leads to this minimization problem. So then the question becomes, how do we solve this, or find b hat ml? So one thing that you could certainly do, and it's a pretty good thing to try, is to set derivative to 0. So basically, we know that minimizers for it should hopefully be points where the gradient is 0. So gradient of f of b is 0. And so remember that okay. Okay, and so let's set that to 0. So, or let me just... all maximum likelihood, a necessary condition, I should say. Okay. So this is a necessary condition for a minimum. And in general, and so what we have here is that so let's take derivatives of everything. So the sum of derivatives is just you can bring the sum inside each term, and now we can use the chain rule. We have xi transpose b, and so the xi just comes out the front here. You can do this if you're not comfortable with this vector notation. You can do it term by term. So for bj, the only coefficient is xji, and so you can bring that out, and then that's gonna very nicely just work out to be xi transpose b. Okay, and then that's going to equal to this is just a linear term, so that's just going to disappear, and we're just going to get xi times yi. And you can see that this is p by 1, and this is p by 1 here. So I should say that this is at the solution point. Okay, so we have p equations with p unknowns. So let's look at these in some specific examples here. So for the linear model, we have that normal and so this is where we're going to really use everything that we've kind of learned in the previous couple of lectures, and sort of forming these connections is going to be really important in sort of following what's going on when we're going to kind of switch interchangeably between distributions and log partition functions and so on. So for the normal distribution, so we have that yi is we're going to say normal xi transpose b, and then for simplicity we're just going to let 1 be the variance, so sigma squared equals 1, and it's a known fixed constant. So you might recall that for the normal distribution, a of theta equals theta squared over 2. And therefore, the derivative very conveniently just works out to be theta. And so if you plug that in here, you're just going to get the a just disappears because it's just the identity function. So we're just going to get we can write things out like this, and then you can also hopefully see that in our matrix vector form, so we get exactly back to, these are the normal equations. And so this is really nice. So just, this is not, anything new. It just confirms what we already know. And we know that this leads to closed form solution. Because we have a linear system. So because we have linear systems, so we have p equations and p unknowns, as I mentioned earlier. But now we have, and if it corresponds to a linear system, so I'll just remind you that here x is in r to the n by p, and y is in r to the n. Because we have a linear system with p equations and p unknowns, we understand that very well. We know how to invert linear systems and so on. So this has a closed form solution. Okay, so now let's focus on some other examples. So if we look at, let's remind ourselves of the general equations here. So if we look at, the other example of, yi is distributed Bernoulli, and then we have this 1 over 1 plus e to the negative okay, so we have this Bernoulli distribution. In that case, we have that a of theta is log of 1 plus e to the theta. And so our a prime of theta is equal to 1 over, or e to the theta over 1 plus e to the theta, which is 1 plus e to the negative theta to the negative 1. Okay, and so what we get if we plug that in is that okay, so note here that we have, this is nonlinear equations. And in general, and if you can talk to people in kind of, algebraic geometry or or analysis who've kind of spent a lot of time studying these kinds of nonlinear systems of equations, say that there's typically no closed form solution here. So really this is what I've written down here is the furthest we can really go. And we'll come back to that later. Now let's finish off with another example to see kind of what happens in the other case we've focused on a lot, which is the Poisson case. So I'll write down the equations again. So in the case where yi is distributed as Poisson, and then we have this, that this is e to the, okay. No. then we know that for the Poisson that a of theta equals e to the theta. Hopefully, as I sort of say these things more and more, this will become more and more kind of second nature in terms of thinking of each distribution in terms of its log partition function, and because that's such an important property. And so we know that a prime of theta equals e to the theta. And so the equation you get, as we see, is again going to be something pretty nasty, nonlinear set of equations again. Okay, so again, we get a set of nonlinear equations with no real set of no closed form solutions. So once again, we have p equations and p unknowns, but these are nonlinear. So we can see that these are the general equations we get for the GLM. So we have p equations and p unknowns, but we have this kind of potentially complicated nonlinear equation here. So this leads to various questions like how do we find beta hat ML, and then this also leads to questions of does a solution exist? So there's various questions that kind of arise here because of the fact that we now have a system of nonlinear equations. So for the case of linear models, things worked out really nicely because linear models, we live in kind of a system where we live in kind of a world where everything is linear in linear systems, which we know a lot about. But as soon as you move away from linear systems, which you do for generalized linear models, because this log partition function, the derivative of that is not necessarily linear, then we kind of get into some challenges. So I'll get to that shortly. I just wanted to quickly touch on So we saw in the previous lecture that there's a very nice connection between maximum likelihood and method of moments. And so let's kind of look at these equations now and think about some properties we know about exponential families and how that connects to these. How it connects to potentially method of moments and what we already know. So recall that we know that theta of I equals xi transpose b, and equivalently theta hat ml of I equals xi transpose beta hat ml. And then we also know that E of yi equals to equals a prime of theta of I. So what we have here is this is actually so this is actually equal to the expectation of yi if theta hat ml is equal to xi transpose beta hat ml. So you can kind of think of this as, so an interpretation of these equations is that you're kind of matching the expectation of yi to yi, where the expectation is taken, or the parameter okay, so this is just kind of another interpretation of how this this maximum likelihood procedure ultimately also leads to kind of a method of moments the set of equations we might get if we used a method of moments types of procedure. So just to kind of give you just a sense of where a bit more insight into where these equations come from. So now we return to the question of so then the question is, how do we find B hat ML in general? So, we don't have this nice set of linear systems anymore. So we can't just kind of use what we did for when we had linear systems, where you just have to invert linear systems. Now we have nonlinear systems, which are extremely difficult to solve or invert. So recall that our goal, I'm going to write this in terms of the original formulation. So this is our f of b that we're trying to minimize. So one thing to note here is that we know that A is strictly convex. So that obviously, and so what this also implies is that is also going to be strictly convex. So if we, so I should say that this is not actually true. It's guaranteed to be convex because, it's also guaranteed. It's guaranteed to be convex, and the reason for that is because if we look at the derivative, we've just got a linear. So this is convex because it's the composition It's a composition of a convex and a linear function. So this is also convex when you subtract off the xi transpose by, because this is linear. And when you take second derivative of linear functions, they just become 0. So that doesn't really change the convexity properties. So the convex plus or minus linear. You can check all these properties yourself by kind of taking double derivatives and see what you get. So we're still convex. And then the final thing we note is that, when we start taking these sums, then this is still convex. So this is our f of b. This is convex since the sum of convex functions is convex. So we're using kind of this nice calculus of convex functions, which basically allow us to conclude that so we have that f of b is a convex function, and so what that means is that if the gradient f of b is a minimizer. Note that we, may not be unique, but it's but still is a minimizer. And so what we can say is that so remember that when we took derivatives equal to 0, so any solution that satisfies that ensures that beta hat ML is a minimizer of f of the function f of b. Okay, and so what that means is that so that's already pretty cool. And the other thing that's pretty cool about this is to find beta hat ML, we are simply minimizing a convex function. And so this leads to the world of convex optimization. So there's, hundreds of books that have been written about convex optimization, because when you're minimizing convex functions, that's something that's actually pretty nice and has a lot of cool properties. There's also a number of courses, both at grad and even undergrad level, on convex optimization. And so because of that, we have convex optimization provides plenty of tools for minimizing f of b or finding b hat ml. Okay, so for linear models, we invert linear system. So for linear models, we have to invert a linear system, which is which leads to tools from numerical so here I'm talking specifically about how we find solutions. And so remember that for linear models, when we did least squares, we always ended up with these normal equations or something like these normal equations. And so the challenge there was you always had to invert a linear system. And so there's many, inverting a linear system is a very well studied problem in math. And numerical linear algebra gives you many tools for how to solve it. And the other thing that was nice with linear systems is we got a closed form solution. As we saw here, we don't get for GLMs, we need to minimize a convex function. To find maximum likelihood estimate. And that leads to tools from convex optimization. So I just kind of wanted to just take a step back and talk about this, that what's kind of nice here is that we start with very statistical problems and statistical models. And then, we ultimately have to kind of solve. We have to actually find these either exactly or numerically. And it turns out that kind of these different classes of problems, firstly the linear models, and now the generalized linear models, which are statistical models, kind of lend themselves to this lends itself to different optimization tools. So for the linear models, this led to the optimization tools of numerical linear algebra. So things like for inverting linear systems, I talked about Gauss-Jordan elimination and then gradient descent, but there's lots of other tools in that field too. And now for GLMs, we have convex optimization. And again, that you could teach kind of whole courses on this, and people do. And it's pretty interesting, and there's lots of nice things. It's one of the more useful courses I think you could probably take, convex optimization, because it just comes up everywhere. But we can kind of leverage these tools to solve the problem. So it's kind of nice how we start with statistical models, and then we end up with a set of optimization tools to kind of find solutions. So just to just sort of recap where we are in the framework. So one, we have the data. Okay, and then we can again write this in vector notation. Where we express things as picovariates and just in one response. And then for the GLM, we have that so we have again B is our parameter of interest, which is the coefficients of these covariates, and then importantly, P is exponential family distribution. And so I'll just write it out. So we have that where theta of I is x of I transpose B. Okay, and so this was this is the data generating so this is the data generating model. And then 3, which was the estimator algorithms. If we use maximum likelihood, we have that okay, and so this F here is convex, and so this leads to tools from okay. So in the next lecture, we're actually going to go into one of the tools, which is one we've already seen before, which is gradient descent, to actually get into the nuts and bolts of how you might try to solve some of a set of equations like this. But note that there's a number of different tools, and I'll just briefly mention some of them in the next lecture, because we've realized the fact that finding a solution is equivalent to just finding the minimizer of a convex function. This leads to a whole set of really useful tools for finding such a solution. And so, the maximum likelihood, although we don't have a closed form solution for it, we have a lot of good numerical ways to find good solutions. Okay, so that's it for today, and we'll continue on with this discussion in the next lecture. Thanks very much.